Hi everyone, welcome back. Today we're going to talk briefly about ions and molecules and spend most of our time on Avogadro's number. The learning objectives for today include using Avogadro's number and the mass-mole relationship to be able to calculate how many atoms or molecules there are for a given number of moles and vice versa. Atoms are usually found within molecules or extended networks. Very infrequently do we just have one atom floating around in space. What happens more so is that they form these groups. These groups are called molecules. And these are different representations. So these are the same thing. And they're just different ways of representing the molecules. But what we see is this is actually a group of 5 atoms, this is a group of 4 atoms, and this is a group of 3 atoms. And these groups are called molecules. If we have ions that come together to form interactions, those are called ionic compounds. And ionic compounds are different in that they can repeat on for a long distance relative to the size of a molecule. And so this, it actually repeats on and it repeats on out in three dimensions. The reason why we need to talk about this is because today we're going to learn about Avogadro's number and look at millions and millions, in fact billions and trillions of molecules and atoms all at once. Molecules and ionic networks form due to the rearrangement of electrons. The nuclei, the number of protons and neutrons, don't actually change, but it's the electrons that do all the chemical work, and that's going to become important later on. So we can represent molecules in different ways. This is the molecular formula of a molecule. This is ribose, which forms the backbone of DNA. We can also look at ribose in terms of its structural formula, in terms of a ball and stick model, and a space filling model. And it turns out that the space filling model is really what's most accurate in terms of what they actually look like. And we'll get more into that later. But the point here is to see that we can represent molecules in a variety of different ways. For now, we're going to focus on the molecular formula. So we talked a little while ago about AMU, the atomic mass unit, and how this is involved with atomic weights. And it has an equivalent mass in terms of grams. If we inverse this relationship, we can solve for 1 gram, and we see that 1 gram is equal to 6.022 times 10 to the 23 AMU. And that number hopefully is a little bit familiar. If you have heard of Avogadro's number before, Avogadro's number is based on this relationship. And it's the number of things that there are in 1 mole, M-O-L-E. And so a collection that has Avogadro's number of objects, and that can be atoms or molecules or electrons or hair particles or balloons or your friends, that's called a mole. So if you could have 1 mole of cars, that's equal to 6.022 10 to the 23 cars. This is similar to how 1 dozen equals 12. So it's just simply a unit, a certain number of things. To give you an idea of scaling, 1 gram, 10 grams is approximately the weight of 1 pencil. So there would then be 6 times 10 to the 24 AMU is 1 pencil. And so this is very, very, very small scale, the AMU is. And this is more, think of it, the macroscopic scale, the world in which we live. And again, as I point out here, it's important to note that this is not just a number, but it's a number per mole. Okay, so another way of writing this is 6.022 10 to the 23 per 1 mole. And this could be of anything. So if you had a mole of atoms and you weighed them out, the same number of grams is equal to its atomic mass in AMU. And that sounds really confusing, I know. But let me explain what that means. If you have 1 mole of carbon, that weighs 12.0107 grams, and it contains Avogadro's number, 6.022 10 to the 23 atoms. If you have 1 atom, then that would be the 12 AMU. So we see that there's a relationship between the mole, the atom, and grams and AMU, as we've said before. If we have 1 mole of ribose, the sugar we talked about earlier, that weighs approximately 150 grams and contains Avogadro's number worth of molecules. So 6.022 times 10 to the 23 of these. How we get this is by using the molecular formula and multiplying times the atomic mass of each of these. So in the molecular formula, we have 5 moles of carbon. Each one of those from the periodic table weighs 12 grams per mole. That gets us a total of 60 grams. We have 10 hydrogens. Each one of those weighs approximately 1 gram per mole and gets us 10 grams. And then we have 5 moles of oxygen, each one weighing approximately 16 grams per mole, and that weighs 80 grams. And again, all of these numbers here come from the periodic table. If we sum those up, we get that the total mass is approximately 150 grams, and that is per mole of ribose. One molecule of ribose again would weigh approximately 150 AMU. Okay, so they're interchangeable. Now we can connect mass moles and the number of particles through Avogadro's number and the molar mass. The way that this works is if you have a certain number of particles and you divide by Avogadro's number, you'll determine the number of moles. Conversely, you could go the other way. If you have the number of moles, you could multiply by Avogadro's number to find the number of particles. From moles, you could also multiply by the molar mass and determine the number of grams. Or if you have the number of grams, you could divide by the molar mass and get moles. This relationship, you essentially will want to know. And through practice, it will become very intuitive, very second nature. So let's practice. Here's a problem. I'll walk you through this one. If we have, so sugars used to make soda have the molecular formula C6H12O6. And a typical can of soda has 39 grams of sugar. So how many moles of sugar are in 1 can of soda? Well, the way to solve for this is by determining the molar mass of the sugar. And the molar mass of the sugar is found by multiplying the number of carbon atoms times its molar mass, or atomic mass, molar mass, adding the number of hydrogen atoms. So this is 12 hydrogen atoms, and each one weighs 1 gram per mole. And then add to that the molar mass of oxygen atoms. And there's 6 oxygen atoms in the molecule. That gets us a total of 180 grams per mole. This is the molar mass C6H12O6. And if we want to know how many moles there are in 1 can of soda, we can just take a ratio. We know there's 39 grams of sugar per can, and if we divide by the number of grams of sugar per mole of sugar, what we see is that the grams of sugar cancel out, and then taking this ratio and rearranging the units, this will go on the top, this will go on the bottom, and this goes on the bottom, this goes on the top, and we end up with 0.22 moles of sugar per can. That gets us then our answer, more than 1,000th of a mole, but less than 1 mole. Okay? Now, you get to try. Pause here, try and solve this on your own, and then we'll come back together. All right? Since we know that there's 0.22 moles of sugar per can, we can multiply by the number of cans per pack. That will then cancel out the cans. But we want to know how many sugar molecules there are in a pack. So we need to then use the relationship between molecules and moles, which is Avogadro's number. If we solve for that, we get 1.6 times 10 to the 4 molecules of sugar per pack. One last one. Pause here and try this on your own first. All right, how many hydrogen atoms are there in 25 milligrams of ibuprofen? You're given the molecular formula. We can determine the molar mass by adding together the mass of all of the carbon atoms with the mass of all of the hydrogen atoms to the mass of all of the oxygen atoms. That gets us a total of 206.29 grams per mole. We know we have 25 milligrams. We need to convert that from milligrams to grams. We can then use the molar mass of ibuprofen and we see that we have 0.000121 moles. This, however, is of the ibuprofen. We want to know how many hydrogen atoms there are, and so we need to convert to molecules and then use the ratio of number of hydrogen atoms per molecule. Okay, again, this is Avogadro's number, and this is the number of atoms in the molecule. That gets us 1.3 10 to the 21 atoms. Okay, so we looked at this carbon atom before, and we talked about how there's the nucleus in the center and the electron clouds outside. But it turns out that knowing where the electrons are is actually a question of energy. And this question of where are the electrons is important because it affects how elements will react with one another. So next time we're going to be looking at energy and how that can help us to understand the reactivity of elements. Thanks for watching and have a good day.